Craig, if you take this promotion, you'll have to manage people, track budget and schedule, do people's performance reviews, approve time cards, work a lot more hours, and you'll get a little raise, maybe 5%. But you'll get to join the annual profit sharing program. I've been in it for 7 years, and it's paid out twice in that time.
You know, I think I'd rather just go back to my desk, space out, and listen to this Fungineering podcast.
All right, so today we're talking about nuclear weapons, right?
I guess so. Blake's going to talk all about different types of nuclear weapons, and then we're going to talk a little bit about ICBM defense and why it's a sham and you should put no faith in it.
Short the stock.
Buy puts against it. Long dated, low strike price.
So, I think you wanted to tell a story about some liquid nitrogen?
Okay. Yeah. So, when I was at NASA, we had Building 32 and Building 33, and these were the environmental test chamber buildings. And I kind of hope that somebody who still works there will go by and kind of verify if it's still this way. Building 32 contained Chamber A and Chamber B. Chamber A is this giant thermal vacuum chamber. It's 7 stories tall inside. It's the second or third largest thermal vacuum chamber in the world. And then Building 33 contained a whole bunch of much smaller chambers for testing smaller items. So all of these chambers can pull a hard vacuum and then cycle liquid nitrogen through them to make it really cold, turn on heat lamps to make it really hot. And so it simulates a space environment. And Building 32, with the 2 very large chambers, it has this big liquid nitrogen tank farm outside of it, with, I believe, 6 very large tanks for holding liquid nitrogen. And Building 33 just has a single large tank.
What's a very large tank?
Say 25 feet long and maybe 8-foot diameter.
So like it would be on the back of a truck?
Yes, except these are stationary tanks, I believe.
It's pretty big.
Yeah. And the reason they need to store so much liquid nitrogen is they run the liquid nitrogen open loop. So when they're cooling a test article or they're cooling the chamber, they just pass the liquid nitrogen over it and then it's caught and it goes out to a flash pan and it just boils off and it's lost. They don't have the refrigeration capability to chill it back down and cycle it back through. So,
could you explain to our listeners what the liquid nitrogen loop is for?
You mean to cool the test chamber?
Yeah, I didn't understand that initially when you described it to me.
Oh, so it's 2-part. One is it simulates the cold of space, and 2 is it actually helps in making the vacuum better. Because if you have a flat plate inside a vacuum, and that flat plate has tubes inside of it that have liquid nitrogen flowing through them, the whole plate will get very cold. And when you have random atoms still bouncing around inside the chamber that's mostly a vacuum, when they hit that plate, they stick because it's very cold. So you can actually get the vacuum a little harder by putting the cold plate in there.
I guess you only pull nitrogens out of the air, right? Not oxygens.
With that plate, I'm not exactly sure what sticks to it. Do you have a chemistry-based theory on why nitrogen sticks and oxygen doesn't? I don't know. It's pretty cold.
Pretty cold.
I mean, this is how technical we are.
It's hard to breathe in there.
Very hard. And no one can hear you scream either.
That's true.
So the purpose is twofold. And then also we had some other chambers where we would just use it to cool the environment, but it was not pulling a vacuum. And so in those cases, there would be a fan at the top of the chamber, and there would be a slow drip of liquid nitrogen that would just fall over the fan. And when it would hit the fan, it would just flash and mix with air, and it would cool the air a lot. And so you would cool this chamber down by dropping liquid nitrogen over this fan.
Don't you also make it not a vacuum chamber then?
Yeah.
Oh, okay.
Yeah, these were non-vacuum chambers in that case.
Okay.
So all of these chambers were open loop, though, with respect to their liquid nitrogen usage. So, like I said, we had no ability to capture the liquid nitrogen, re-refrigerate it, or cool it back down, remove the heat from it, and use it again. So it was just wasted afterwards. So we would have these situations where especially running chamber A and chamber B, since they use so much liquid nitrogen, if you were running chamber A, this very, very large chamber, you basically needed a continuous stream of trucks coming in, bringing liquid nitrogen and offloading it into the tank farm. And at some point, somebody decided, hey, and he was a civil servant engineer there. That's as much blame as I'll assign. The best stories are the civil servants.
Truly.
He decided, what if we're doing something and either building 32 or building 33 needs liquid nitrogen and they're running out, but the other building has it. And let's build a pipe that goes between the buildings to hook up the liquid nitrogen systems of the two buildings. Mm-hmm. And you know, the 6 tank farm in building 32 can supply the 1 tank in building 33, and they can back each other up, and it would just be a little bit of redundancy. And it's kind of an okay idea, because when you get chamber A pumped down, it costs a lot of money. All that liquid nitrogen, all the manpower, all the electricity to pump it down. The costs that you would get quoted if you needed a test done in chamber A was about $100,000 to get the chamber pumped down to a vacuum. And if your test article had some kind of problem then, and they had to bring the chamber back up to atmospheric pressure and fix your test article and then pump it down again, you were on the hook for another $100,000 to pump it down again, because the power and material requirements were so high. So, you know, it kind of made sense. Let's give a little more redundancy there for the liquid nitrogen part. Since it's open loop, we're losing it all. So he designs this system, and it consists of a pipe in the parking lot between the two buildings. It's suspended about 8 feet in the air, and it's got what's called vacuum jacketed piping, which means that you put this special outer pipe around the liquid nitrogen pipe, and then within that outer pipe you can pull a vacuum, which is a very effective way of insulating. It's also very expensive. So we would typically say that if you needed to run vacuum jacketed piping, it would cost you about $100 a foot to run it, to install it. You know, and this is probably about a 400 or 500 foot run across a parking lot between the two buildings. Now, this is in Texas, and Texas has summers and they get hot, and, you know, it can easily get into over 100 degrees. And this vacuum jacketed pipe, though it was vacuum jacketed, it was not then shaded or anything. So it's just vacuum jacketed pipe sitting out in the sun in Texas, you know, in the summer. And they install this whole system. It costs several $100,000 and takes a bunch of time. And they hook it up between the two buildings, and everything's done. It's all signed off, which is, you know, a monumental hassle at NASA to get any type of project, infrastructure type project done. And, you know, they're patting themselves on the back and they say, all right, let's switch it on and let's transfer some liquid nitrogen. And they turn the thing on. And so they power it from the building 32 side, where they have this huge reservoir of liquid nitrogen. And then they open the valve on the building 33 side, where they want to receive liquid nitrogen, and they sit and they, you know that it's going to take a few minutes for the whole thing, the pipe to cool down, and they've drawn a vacuum in the vacuum jacketed pipe, and they're waiting a few minutes, and, you know, they're getting nitrogen gas out. And, you know, when liquid nitrogen flashes to gas, I believe it increases in volume 700 times. Mm-hmm. So they're getting quite a bit of gas coming out, and they wait a while, and they wait a while longer, and then, you know, they get kind of bored and they walk away, and they just leave it running for hours, and nothing happens, and they eventually have to go home, so they turn it off, and the next day they come back, and they're like, well, it all warmed up and everything, pull the vacuum on the pipe again, turn it back on, we'll run it all day, and we'll get it going this time. And they leave it running all day, and not a drop of liquid nitrogen ever flowed through that pipe from one end to the other, ever. And all of this happened a few years before I came to work there. So this was all a story related to me when I was working there starting in 2006. And even then, that elevated pipe, vacuum jacketed in all its $100 per foot grandeur spanning across the parking lot, stood as a monument to failure. And I bet it still stands there today because it would be an equally big problem to have it torn down.
I've always heard that failure was not an option. So, was it just failing to cool down the internal pipe? If you ran it indefinitely, would it eventually work?
I suspect no. I think that there was so much heat gain just by the nature of this suspended pipe outdoors in the sun that over the whole long run, there was too much heat gain and the liquid nitrogen could not absorb that much heat without flashing to vapor.
Did anyone go outside and put their hand on the pipe?
I don't know.
Or look at it with a thermal camera? That would have been pretty interesting.
Yeah. See the gradient from one end to the other.
Yeah. The thing that amuses me so much about it is the idea of connecting 6 tanks to 1 tank. It's like, you know, if you have a gasoline-powered mower, and so you connect a little hose to your car's gas tank, and that way if your car needs a little extra gas, it can pull it out of the mower, you know? Then you're good. Or maybe you do it with a truck, so you have your mower in the bed. You're like, but what if I need a half gallon of gas out of my mower? Well, we got you.
I need a quart of gas to top off my 30-gallon truck tank.
Or what if you can't just, you know, siphon it out of the truck easily and put it in the mower? There's a hose, so you're good.
Had I ever told you that story?
It sounds familiar. I didn't remember it.
Okay. Let's move on to a more optimistic subject, nuclear weapons.
Hey, I think nuclear weapons are really cool. The downside is they're a weapon, and
something where we at least have engineering success.
yeah. And, you know, mostly they're to kill people, so that sucks. But they're just such a singular technological achievement. They're up there with rockets and certain other unusual things. So, to start off with, do you have any questions about nuclear weapons?
So I think that I may not know enough to ask good questions yet until we get into the subject. So many, many, many years ago, I got a bachelor's degree in physics, and we talked about some nuclear physics at some point, but we never got into subjects of here's something applicable. Here's how nuclear weapons work. And so it was all much more vague things, you know. Here's some basics of nuclear physics, but, you know, it's mixed in with a whole lot of other undergrad subjects of physics. And so why don't you go on and
Just go on.
And I will ask questions.
Okay. So, when I talk about nuclear weapons with somebody who's interested...
Oh, I do have one question.
Oh.
Are gun and implosion type weapons both fission weapons?
There are fission weapons that are in both configurations. Or there have existed.
Okay. So were Little Boy and Fat Man, was one a gun type and one was an implosion type?
Yes. So, the first atomic bomb detonated was the Trinity test by the US. And that one was an implosion type device that used plutonium. And the second detonation was the Little Boy in Hiroshima, and that was a gun type using uranium. And then the Nagasaki device was identical to the Trinity device, and so it was another implosion plutonium bomb. And all of those were fission bombs.
So the Hiroshima device was essentially a untested device?
Yes, they had such high confidence in it working that they didn't test it. And considering the device cost on the order of like $1 billion, they didn't really want to test it. They didn't really want to do the Trinity test, but they weren't that sure that implosion would work because it's very complicated and finicky, which I'll try to get into, but without boring anybody.
Okay.
Yeah, so, yeah, it's a little weird. There's 2 different bomb types. Gun type is kind of unsafe because there's a lot of ways for the bomb to fail in a like fail deadly type configuration. There are different ways that the 2 pieces can get slammed together, like through accident or misfire or whatever, and then you get a critical yield that's not necessarily the maximum yield, but it's still extremely dangerous.
What are these 2 pieces that are getting slammed together?
In a gun type weapon, there's 2 pieces of uranium, and I think commonly the image that's portrayed in a diagram is either there's two hemispheres or there's like a sphere with a cylinder cut out of it. And the two pieces fit together to form a sphere. And so you'll have like the target and then the projectile, and the projectile is fired via explosive into the target. And so it temporarily forms a critical mass. And I think maybe it's not known how the little boy worked even. I don't think they've ever revealed what the specific shape of the uranium was. I think that's still like a top secret.
Does it have to be fired, or would just bringing them together be good enough? Do they have to be brought together very quickly?
Yes.
Okay, I think the thrust of that question is, when they're brought together, is the proximity what's important, or is it pressure from them being pressed together that's important?
Okay, so you're getting into one of the two things that makes nuclear weapons really hard. So I guess I'll talk about that one first. So one of two reasons that it's very difficult to build a nuclear weapon, and it essentially takes nation-state resources, is because even if you have a critical mass of uranium or plutonium sitting around, I don't know why you have this. Let's say you have it in your backyard, just a bunch of weapons-grade plutonium or whatever. If you pile it all together into a critical mass, then it will start a criticality event. Essentially, an atom is fissioning and it's releasing a neutron, and that's hitting another atom and releasing a neutron, and it's happening at a rate where it speeds up instead of slowing down. And so that means you're critical. Criticality happens when you're 1-to-1.
And these are unstable isotopes that are just radiating neutrons out, right?
Yes, they just periodically fizz. That's what a Geiger counter detects.
Okay.
Those little clicks are neutrons hitting it. I think that's right. I hope I'm not wrong and it's like gamma rays or something, but I believe that's what it is.
And not to stray too much further away, but can you explain what an isotope is?
An isotope is when you have an element and it has its correct number of protons, because that's what gives it its identity as an element, but it has a different number of neutrons than, well, actually, you can have a stable isotope. So isotope just refers to how many neutrons does your atom have. And so you can have different amounts of them. And I don't understand why some nuclei are stable and some aren't. I don't know what rules govern that. But essentially, if you have any isotope of uranium, it's unstable. And if you have any isotope of plutonium, it's unstable. And to different degrees. So uranium-238, which is the natural kind of naturally occurring uranium, is really stable. It has a half-life of, I think it's 4.7 million or billion years. It's an extremely long time. So it just doesn't emit very many neutrons. And so it's not very useful for trying to start a chain reaction. But in natural uranium ore, 0.7% of it is uranium-235, which has a half-life of, I need to look that up, but I think it's something like 88 years. So it's fissioning all the time. You'll have many, many atoms of it just sitting around. And so it's just emitting fissions all the time, firing off neutrons. And so it's very happy to go critical if put in the right circumstances.
Okay, so if you get a whole bunch of uranium-235 together, then they're all just happily shedding neutrons, and they start hitting each other, and that induces them to shed more neutrons?
Yeah. And so then you have this cascade. And it happens on the order of microseconds. So the problem is, whenever an atom or a nuclei of uranium or plutonium undergoes a fission event, it gets extremely hot. You can imagine that a neutron's hitting the nucleus, splitting it into two, and then both resulting new nuclei ring like a gong. If you imagine that everything is like springs or held together by magnets or something like that, it's not the worst analogy. It kind of acts that way. When you split it apart, they fly apart at a very high speed, and they both have a great deal of vibrational energy. And so you can view it as like the nuclei get very angry by being split. And that's a lot of heat. And so then they will bounce into other non-fissioned atoms and heat those up too. And the amount of heat released is on the order of millions of degrees in a nuclear explosion. And so the problem that you run into when you have this runaway criticality event is your radioactive material gets hot really, really fast. like on the order of microseconds. It gets super hot. And so all of it wants to turn into a gas, and all of it wants to expand in every direction away from itself. It also gains a charge that makes it try to repel itself. So whenever you start having a critical mass of fissioning material, it very badly wants to fly in every direction away from itself. And so one of the two really difficult things about constructing a nuclear weapon is trying to get that material to stay together long enough that very much of it undergoes fission. It's very easy to get it to stay together long enough that it heats up to a few thousand degrees, and then it blows up, but in a not particularly destructive way. And that's what happens with like nuclear reactor accidents. Those blow up, but they're nothing like, there's no mushroom cloud. They're nothing like a nuclear bomb. And they couldn't even be that way if they wanted to, because they're not designed specifically to mash all the material together for that brief instant of time.
And are the samples not pure enough?
That doesn't matter as much. Criticality is a matter of how much material you have, but also its configuration. So if you have a critical mass, like if you have a critical spherical mass of plutonium, but it's in like a torus shape, it won't actually go critical because it's not able to hit itself with neutrons fast enough to sustain a critical reaction. And so that's why spheres are chosen, because they're optimal for that. Or actually now they're like ellipsoid egg shapes. And in a reactor, all the fuel is in a whole bunch of rods. So it's purposely kept apart from itself so that it can't ever really get too hot. Sometimes it happens.
And is that also to try and create more surface area to transfer heat to the water to eventually run a turbine, etc., in a reactor?
I don't know. That's an interesting question. I haven't studied nuclear reactor design almost at all.
Because ultimately what you desire from the reaction in a nuclear reactor is to heat up a bunch of water.
Yeah.
So if you have a whole bunch of long rods, you'll have a lot more surface area to volume.
Yeah, that's about right. And in a nuclear bomb, what you want to do is heat up all the air around it a whole lot. So, I don't know. I know there's other things like pebble bed reactors where the fuel is enclosed in spheres. And I think that the RTGs in space probes use spheres. I think rods might just be because it's easy to machine and work with, and you can move them up and down and stuff like that. You could probably build one with like cubes or dodecahedrons or some other goofy shape, and I think rods are just easy to work with.
Okay.
So one of the primary difficulties is assembling your radioactive material. You want it to be as close to itself as possible for as long as possible. And once you've assembled it into a critical mass, it's immediately going to start fighting you and trying to fly apart. And that's why if you've ever read about the yields of these weapons and how much energy is in the materials that are in them, the yield is usually something on the order of a few % of what the material is truly capable of. So like the Fat Man bomb, I think had something like a 1% yield, given that it had that much plutonium in it. And for the most part, I don't think anyone's ever going to figure out how to make some kind of magical 100% yield bomb, because you'd have to hold this material together for an inordinate amount of time to get all of it to fission.
They did it in Stargate.
With Naquadah?
Yes.
Or Naquadria?
Naquadria was the reactor, I thought, or what the reactor ran on.
Naquadah is their fictional material, and it boosted nuclear weapons a huge amount for no discernible reason. And Naquadria was the material they found on this one planet that had an effect that was orders of magnitude more powerful than Naquadah.
Okay.
And then that planet had a little allegorical parable of their own where they, I don't know, blew a crater in their planet with a Naquadria bomb or something like that. I don't know. Maybe it was a teachable moment or something. But anyway, commentary on nuclear bombs. So yeah, the reason that you have like a gun type or an implosion type is just because you gotta assemble the thing together and make it as dense as possible, as fast as possible, and then the material does the rest. So with gun type, you're just putting it together for the most part. And with implosion type, what you're doing is taking a sphere of material and compressing it against itself. So you'll have a sphere of plutonium and you're just trying to make it denser. So you're just mashing on that plutonium. And you might think, plutonium's a metal. How much can you really compress it down? And the answer is you put roughly 5 feet of explosives around it in the case of the Fat Man bomb, and then set all those explosives up to blow up in a perfectly spherical configuration, and they can mash the plutonium down quite a bit. And that's why it blows up.
So when they take that plutonium core, they don't particularly build the core with any hollow area in it. It is a solid core to start with, but it's just not enough to on its own be critical.
No, it's more complicated than that. Pretty much everything about nuclear weapons is always more complicated than you think it's going to be. So a core, or the pit of a nuclear weapon, will be hollow, and it'll contain an initiator inside of it. And initially what they used for initiators was this mix of polonium and beryllium, and they were in this very special configuration, and it's very complicated. There's no way to describe it without a diagram. But they called it an urchin, because it was sort of spiky, in a way. But the point of the initiator is it's a neutron source. So when you mash all your material together, you want there to be a lot of neutrons in the center. That's the ideal place for your blast to start. If you imagine trying to blow up a sphere of explosives, you'd probably want to put your detonator in the center of the sphere, because you'd get the best explosion characteristics. And here your detonator is neutrons, so you put your initiator in the center. So then you have your core, which is roughly spherical, but it has this hollow bit. And around that you have a tamper, and the tamper is a neutron reflector. So that, again, enhances your detonation characteristics. Once you start making neutrons, you want as many of them to hit the uranium or plutonium as possible. We'll just talk about plutonium bombs for this.
Okay, so, but the tamper is to reflect back into that beryllium core?
No.
To keep that reaction going?
So you have your initiator, and it's in the center of your sphere.
Mm-hmm.
Then you have your sphere of material.
Okay.
And so your sphere is really dense, so like neutrons aren't getting through that. And then around that, you have your tamper.
Okay, I'm sorry, I thought the tamper was in between.
No. So
Okay.
The tamper is outside of the sphere, and it's to reflect neutrons. And so then, since you're trying to crush this sphere really hard, you run into these different issues with timing and synchronization of your explosives and irregularities about how that works. So there's another pusher around that. And that basically just serves to gain momentum from the explosives and ram into the sphere in a roughly spherical configuration.
What is that made out of?
I don't know.
Is it like explosives, or is it like steel, or is it some exotic thing?
Pretty much every material is exotic. I don't remember what it's made out of. It's probably some ridiculous thing like, I don't know, lithium or beryllium or whatever. I didn't actually look up what the pusher is.
Okay, but it's not reactive itself. It's simply used as mass to gain momentum and crush the core.
Yeah.
The pit.
Another way of thinking of it is it's more like wadding.
Okay.
And then outside of that, you have your explosive lenses, which I think are this really cool invention. And they consist of a fast explosive and a slow explosive. And they'll be detonated at one point, but the goal of them is to produce an exactly spherical shockwave that mimics the shape of the sphere of what they're trying to compress. So if you imagine something like a soccer ball, and you have a little detonator in the center of each hexagon and pentagon on the soccer ball, if you detonate all those at the same time, you're going to get a bunch of expanding spheres of blast moving towards the center. And so you have to change the way that those waves propagate through the material, so when they arrive, they're a single sphere instead of being a bunch of spheres going the wrong way. Like, you want them to be a concave shockwave instead of a convex shockwave. And so that was one of the complicated issues they had to work out in the Manhattan Project, is how do we make a spherical blast wave propagating towards a sphere? No one had ever had to care about this before.
Mm-hmm.
So once you've done that, then you can smash your plutonium together, and it gets really, really hot, and then it blows up. Oh yeah. Also, the detonators are interesting. So each of these little explosive lenses needs to have a detonator on it. And the detonator has to blow up in a very precise amount of time, because even in a matter of nanoseconds, you will have an asymmetric explosive wave crushing your plutonium. So you have to be like nanoseconds accurate, which is not even a very long length of wire. So they had these very precisely measured lengths of wire running to these very precise detonators that blow up very precisely after current is applied to them. And they're trying to get synchronicity across all of these different things. So that's one of the things where I find a lot of people are sort of confused about nuclear weapons. Like, they think if there's a nuclear bomb and then like 50 feet away there's another one, and the first one blows up, the second one will blow up. like it's a sympathetic detonation or something like that. But instead, nuclear bombs are super fickle, sensitive devices. And if everything doesn't go exactly perfectly, then almost nothing happens. So it took a great deal of effort to smash this sphere in such a precise way that it would give a critical yield and really blow up. And if anything goes wrong, then it's going to produce what's called a fizzle, which is usually sub-kiloton yield. And it's like a waste of a device. So the other thing is this initiator that has polonium in it will degrade over time. And so that was an early constraint on nuclear weapon design. They would have to refresh the initiators periodically. I think they lasted something like 10 months. So they kept having to create new initiators and replace them in the stock of warheads.
And that's the center, that beryllium core.
Yeah.
At the very center?
Yeah.
So then did that favor gun-type devices since you had an open core that was going to try and smash together?
No.
You could already get in there easier? Or did they just replace the entire pit?
They would build the pit in such a way that they could get the initiator out and then put a new one in.
Okay.
All nuclear weapons are basically implosion type. Like, gun type is bad for a lot of reasons.
Okay.
So they're all implosion. There have been a whole bunch of developments. They're kind of hard to go into here because you kind of need pictures. I recommend the Wikipedia article about nuclear weapon design. It's very interesting. But a lot of enhancements have come along in terms of how to build an implosion device. And so now they can be built where they're a few inches in diameter and they still produce the full yield. And it's very easy to make them fusion capable also.
So can you affect the yield by essentially changing the lensing on the explosives or changing the output of the explosives? Or I guess to what degree can you take a bomb that's manufactured and then decide what yield you're going to get from it after it's manufactured?
Okay. So you're basically asking about like a variable yield weapon or dial a yield.
Yes, exactly.
The way that that's usually implemented is in a fusion boosted weapon. And so it's possible to change how much boosting you get. But if you're just building a pure fission device, like if you're building a replica of the Fat Man, there's not a very good way to alter the yield without doing something like just sort of deliberately messing up the bomb. Like, what if I make the explosive lenses fire at the wrong times or something like that?
Okay.
But then if you try to simulate what'll happen, it's very, very complicated. And so it's not a very good way to try and get a dial a yield type of thing.
Okay.
So compressing that stupid plutonium down, that's one of the really hard things about building a nuclear bomb. But when countries attempt to do that, like they hire a bunch of PhD physics students, or I don't know, you could have been one of these people if you just went on and got your PhD in physics. These things aren't super hard to work out. A lot of the information is public. In 1964, they did an experiment called the Nth Country experiment, where they were like, what if we hire 3 college grads who just got their PhDs and task them with making a nuclear weapon with only publicly available information? And after about 3 years, the conclusion was they probably could. So the US was pretty convinced at that point that countries that had the desire to get weapons, they're not going to be limited by technical capability to do so. And in general, that's what we've seen. But, so that gets into the other thing that's really hard about making a nuclear weapon, which is getting a bunch of weapons-grade plutonium. And it turns out that's the actual really hard part. So, in order to get weapons-grade plutonium, first you have to get weapons-grade or reactor-grade uranium. So that's uranium-235. So naturally occurring uranium ore has 0.7% U-235 in it. And that's the good stuff. That's what you want. And with the 238, you mostly just throw it in the trash. I don't know, uranium trash, wherever that is. But you want the U-235. So you have to separate these two things. And the problem is these are only isotopes of each other, as we talked about. So that means their chemical properties are identical. You can really just think of it as light uranium and heavy uranium, like you have light and heavy water. Or there's carbon-12, which is commonly occurring in the environment, and the much rarer carbon-14, which is used for carbon dating. But there's nothing chemically different about these. So there's no chemical process that you can use to separate these. You can't pour acid over them and it dissolves one away or anything like that. So you have to sort the atoms based on how heavy they are. You have to come up with some kind of process for doing that. And in the Manhattan Project, they came up with all the different ways. They came up with 4 different ways and tried all of them for the most part. So they had thermal diffusion, gaseous diffusion, calatrons. I'm not sure if I'm saying that right, but calatrons, and gas centrifuge. They eventually discarded gas centrifuge as not being a workable method, which is kind of funny sitting here in the present because that's basically how it's separated now. It's the only technique anyone uses. But they initially start off with the calitron, which ionizes the uranium and then fires the atoms through an arc with a particle accelerator and really strong magnetic fields. And it tries to make the uranium atoms take the 2 different trajectories that they're going to take. The heavier atoms will go around the outside because they're more resistant to being deflected, and the lighter ones will go around the inside. And then they have a collection bin, and hopefully it's scooping up lots of U-235. It produces very, very little, on the order of, I think it's like micrograms per day with a single calitron, and it's very electricity intensive. It also required a whole bunch of wiring for magnetic coils, so the Manhattan Project went and borrowed several thousand tons of silver from a local bullion repository, because I guess that's the kind of thing that you can do if you're the Manhattan Project. You can just be like, hey, we need thousands of tons of silver. And they're like, all right, make sure you bring it back.
Who's going to sign the receipt?
That's really what happened. They were like, you're going to bring it back, right? And they're like, oh, yeah, we will. And so they did all these ridiculous collection measures, like burned all of the wood that they used to process the silver and then extracted the silver from the ash. But supposedly they returned all but 1/360 millionth of it, a couple ounces. So, good guy Manhattan Project, I guess. So, they use calatrons. They use thermal diffusion, which is where you heat up the material and the lighter atoms diffuse upwards more quickly than the heavier atoms. And they also use gaseous diffusion, which is a similar thing. The lighter atoms can permeate a membrane more rapidly. So they had these different plants that were taking in uranium at the source and then producing slightly more refined uranium-235 at the end. And they eventually had the idea of chaining the plants together and using one's output as another's input. I don't know why that was like a big idea, but I guess no one had ever separated uranium before, so maybe it was a novel concept at the time. So they had a thermal diffusion plant, a gaseous diffusion plant, and a calitron plant. And that let them go from 0.7% to 2% to 23% to 84% U-235. And so by the end of that, they had what you would call weapons grade U-235. And so a great deal of that went into the little boy.
Is there a clear distinction of percentage at which point you count it as weapons grade? Or is that more a function of how competently you can build the rest of the bomb?
Let's go search. Okay, so thanks Wikipedia. It says weapons grade uranium is over 90%. Weapons grade plutonium is over 93%. But yeah, arguably you can build a bomb with a much lower fraction, but you're going to require ever more material. And it's much more cost effective to separate out your good uranium than it is to just use more of it.
Yeah, okay.
So the uranium can either go directly into a bomb, in the case of the little boy, or it can go into a breeder reactor, where you then are making plutonium-239.
You didn't explain gas centrifuge.
Oh, right. Gas centrifuge is a way that was it was waiting for the machining and tooling to be there. Because a gas centrifuge spins at an incredibly high speed, like 100,000 RPM or something like that. It's a very fragile device. So you put uranium hexafluoride gas into it, and then it spins it at a high speed. And in theory, the U-239 gets thrown, or U-238, sorry, gets thrown to the outside, and you can scoop up U-235 through an exit that's in the center of the centrifuge. And it's not that efficient. It produces, I think it's a fraction of a percentage gain in purity, but because of the way it's a continuous process, you can chain a whole bunch of centrifuges together, and each one purifies a little bit in a stage. And you can take the U-238 and pump it like back into that stage. So like stage 0 will have an inlet, and it's a mixture of uranium. And then it has two outlets. One of them is basically heavy and one of them is light. So the heavy gets pumped back into itself and the light gets pumped into the next stage. And so you chain a bunch of stages like that together, and then you can dump out some amount of U-238 from each stage for reprocessing. So basically it gets slightly more pure. You go through many hundreds or many thousands of stages, and at the end, it's pretty pure. And it's pretty cost effective in terms of how much energy it takes compared to all of the other methods. So that's why that's the dominant method now. It doesn't require a super huge plant. It doesn't require as much crazy maintenance. It doesn't require as much crazy amounts of power. It's a lot more practical. But it's still only in the realm of nation states. It would be difficult for Google to build a nuclear weapon and not have anybody notice their vast arrays of gas centrifuges. And it would be really pricey.
And the gas centrifuges are vulnerable to Stuxnet.
Yes. So for people who don't know, Stuxnet was a computer worm that was probably created by the US and Israel in a joint effort. And it hacked into the control systems of Iran's gas centrifuge plants. And it made the gas centrifuges run at either high rates of speed or low rates of speed or pulse between them so that they would hopefully break. And I believe it worked very well. It broke a lot of centrifuges. And that put a real damper on Iran's nuclear program. So you got to separate out all that uranium. Then you put it in a breeder reactor. And then you use that to create plutonium-239. So I didn't do as much reading on that process. It's not as interesting to me. But basically, reactor, plutonium-239.
Oh, I actually have no idea how this part of the process works. I knew everything from the previous part, but I don't know anything about this part.
Well, looks like I should have done more research.
You need to go into even greater detail.
Yep, this is an area where I'm a little hazy. I just didn't research it enough beforehand.
Do you just mash them together?
Yeah, kind of. So, anyway, you have your reactor. It produces plutonium-239. So, that presents its own set of challenges, especially if you're the Manhattan Project. One of the things that I found out in researching this that never really occurred to me is the Manhattan Project started producing plutonium-239. And they're like, yes, this is our material. We're going to use this in an implosion type weapon. And plutonium-239 needs to be separated from other isotopes of plutonium. So it looks like there's a couple.
Okay.
When you want to use plutonium in your weapons, basically you want plutonium-239. So you have to separate that isotope out from the other ones. And basically, no one had ever made plutonium before. And plutonium's not naturally occurring. So the people in the Manhattan Project were faced with this task where they had to figure out how to separate out this material that no one had ever seen before, and no one had worked with, and no one knew the chemical properties of it.
So they didn't know how to detect it once they had separated it out.
They had ideas.
Right.
But it just hadn't occurred to me. I mean, they knew about it, but they're essentially making a new element.
And so based on periodicity, they could have an idea of what it should look like.
Yeah.
But they still weren't sure.
Yeah, they're like, oh, it'll probably dissolve in this kind of acid, and it'll probably alloy with this kind of metal, and things like that. But, like, no one had ever seen any plutonium before. So I hadn't really thought about how hard it would be to say, like, oh, we're going to make some, unobtainium or whatever that no one's ever worked with, and then we're going to try and work with it. And it has to work because we plan to build a bomb out of it, so we have to know exactly what it's going to do. One of the things they ran into, for instance, is that plutonium has different allotropes, which is essentially a different, like, crystal configuration of how the atoms want to line up. So when they were trying to measure its density in order to make it into perfect spheres, they would get different density readings. And it's because it's in these different allotropes. And so they had to figure out a new chemical technique to make sure that it was all in roughly one allotrope so it would have a consistent density. Because otherwise your weapon will blow up asymmetrically and you'll get more like a fizzle than a blast. I mean, that must have been so weird. They're like, hey, let's build all this material that no one's ever seen before. And then they're like, oh, it's weirder than we thought. And then they had to figure out how to fix all those problems. And they would have been trying to go as fast as humanly possible. And it seems really strange. It must have been a weird project to work on. So, anyway. So you end up with this material that now people have seen before. But you have to purify it. And taking uranium ore, processing it to weapons-grade uranium, getting plutonium and processing that to weapons grade plutonium is most of the difficulty in building a nuclear weapon. That's the thing that prevents just anybody from doing it. And a lot of nations have created nuclear weapons programs where they've had essentially a whole device ready, and it's just waiting for the plutonium to be put in it. But they just don't have the plutonium in time. And a lot of times it ends up being years later that they finally have enough fissile material for a device. So that's really the thing that holds everyone up. It's not actually building the device. It's actually getting the material to put in it. So do you have any questions about that?
Not that you haven't already evaded
Thanks.
by saying you weren't ready to talk about plutonium enrichment.
I did what I could. This is a lot of research. I had to refresh my memory on a whole bunch of things that I hadn't looked at in some time.
Okay, so these materials, though, plutonium and uranium, once you get these enriched, are these going to be the same materials for fusion weapons?
Yeah, basically. A fusion weapon ends up just being a fission weapon that is able to ignite some deuterium.
Okay. Is deuterium heavy water?
No, it's heavy hydrogen. Heavy water has heavy hydrogens in it.
Oof. So what's tritium?
I think that's even heavier hydrogen.
Okay. Does it make even heavier water? How heavy can I get my water?
This water is so heavy. I don't know. I don't know if there's a cap. You could take a neutron star and you could fire one proton into it, and one oxygen, 2 protons and one oxygen molecule or one oxygen atom, and then you would have the heaviest water. It'd be so heavy. It'd have all the neutrons. I don't know. I don't really know what the limiting factor is on that. But yeah, deuterium is it's heavy hydrogen, and so heavy water is you have a deuterium in there.
Does it have to be 1 deuterium or 2?
I don't know.
Okay. That's fair.
I don't think you even use heavy water. I think you just use deuterium gas.
Okay.
Because why would you want oxygens mixed in there?
I don't know. I was just watching some World War II documentary the other day, and they were like, here's a show about destroying the heavy water manufacturing facility in Norway during World War II.
Yeah, that was a big deal to try and hurt the Nazi atomic bomb effort. They were going to try and build the bomb. I don't know what their plan was. It looks like... So I was researching what countries had nuclear programs, and it looks like the Nazi program wrapped up in 1942. Essentially, they gave up. They were like, it's not going to be cost effective in time for the end of the war. And so they just gave up. I wonder if they were trying to go straight to a fusion device. I don't think that was ever going to work. But I don't know why they needed a bunch of heavy water.
So can you isolate heavy water and then split it to get deuterium? Is that the plan?
Yeah, I think that's the easiest way to get deuterium.
Okay. So do you want to go on to fusion devices then?
Yeah. So an easy way of thinking of how a fusion device works is it's basically a fission device that generates a large amount of heat, and then that heat is used to temporarily force some hydrogen into a lot of compression while it's really hot, and then the hydrogen fuses. And fusion is a much, much more energetic reaction than fission is. But the way that most bombs end up being built is they use the fusion somewhat to just boost the fission reaction that occurs. Because as we were talking about before, when you're trying to build a fission device, one of the things you want to do is keep the material together for as long as possible. And so if you have an even greater compressing force, or if you can emit even more neutrons, then you can get better fission out of your fission device. And so, like, a fission weapon now, like a modern one that the US would use, is going to be a fusion-boosted fission weapon. And so it uses fusion to get a boost. But, like, people call them hydrogen bombs, but that's not really accurate. It's not really like you're just blowing up a bunch of hydrogen and that's where all the blast is coming from. You're really building this enhanced fission device.
Okay, so something that I never understood. I thought they were like an entirely different class of weapons. Like the engineering was totally different.
No.
And it seems that it just has this added element of fusion in order to boost the fission.
Yeah. Like, I mean, a lot of it's classified by various countries, but if you go look at a diagram of it, it's basically, here's a fission weapon, and here's some fusion core next to it. And they're just like, And they're sitting in styrofoam or plastic or something like that. And that's it. So it's just like, you just put this thing next to this other thing. Boom, now you have a fusion weapon.
So then, by what effect does that boost? Does it increase how hard the fission weapon compresses its core? Or are you using a fusion explosion around the fission weapon to compress the core more and get a higher yield? I'm not understanding the exact method by which the fusion boosts the fission.
It emits a whole bunch of neutrons.
Okay, and so simply sitting next to it is enough.
Yeah.
You don't need some kind of complicated spherical arrangement.
Yeah. You could do that. I believe that's what the Tsar Bomba did.
Yeah, so the Tsar Bomba was this giant bomb that the Russians built just to kind of show off how big of a bomb they could build.
Yeah. And so the term they used for that was, I hope I'm not accidentally saying a Russian swear word or something, but it was like a layered pastry cake. And so basically it was just layers and layers of these. So you can imagine just this arbitrary concentric set of spheres where it's like fission, fusion, fission, fusion, and they all enhance each other.
Okay. And so they would have just gotten a really high yield out of their fission device.
Yeah, basically.
Okay.
Yeah, I thought that too until I researched them. I was like, so they figured out some way to compress hydrogen, but it never occurred to me that the first test of a fission weapon was in 45, and then I think the US's first test of a fusion weapon was in 52. So the fact that these occurred really close together in time should have told me they must be related technologies. And if you look at most countries who have fusion devices, it's fission and then a couple years later fusion. And it's because you need a fission trigger for your fusion device.
Okay, so how do you start the fusion portion that enhances your fission?
So in a two-stage thermonuclear weapon, which is one of the types, this is not the layered cake type, there's a fission core that's basically sitting next to a fusion core or a fusion device. The fission weapon blows up and it's sitting inside of a medium, which will be like plastic or polystyrene or something like that. It sounds like the medium matters, but I don't know in what way. That's still pretty secret. But the bomb heats up this material really, really fast because it's dumping a nuclear bomb's worth of energy into it. And so this material, in its expanding, will compress the fission primary, which is just sitting next to the bomb. But because this material is all surrounding the fusion thing, it's able to compress it in every direction. So the fusion thing will be like a cylinder sitting next to this spherical fission bomb, and it gets compressed in a roughly spherical shape, and it has a bunch of deuterium running down the center of the cylinder. And so this gets compressed, and then you start getting fusion events.
Okay, and so that deuterium running down the center of the cylinder essentially fires out of the cylinder towards the fission device, enhancing the fission yield.
Yeah, it doesn't really fire out, it just blows up where it is. It's like a cylindrical explosion.
Okay.
But then it emits a ton of neutrons, which further boost all of the plutonium that's sitting right next to it.
Okay.
This is one of the places where diagrams would help, but this is a podcast, so sorry.
Okay, so then what kind of yields do you expect out of fusion weapons?
Well, it sort of depends on your device, but those are the devices that see the megaton yields. So like the first ever US two-stage thermonuclear test was 10.4 megatons.
Okay, and how does that compare with Little Boy and Fat Man?
Those were on the order of 20 kilotons.
Okay, so 20 compared to 10,400.
Yeah, so about 500 times more powerful.
Okay.
And it keeps scaling up. Fusion devices are on the order of like 1,000 times more powerful than fission devices, which are already plenty strong on their own.
Okay. Did you want to talk anything about permissive action links and security and those kind of subjects? Or do you think that's worthy of its own podcast?
I haven't researched that enough. That would be interesting if it was its own podcast.
Man, I know a guy.
You know a guy.
He's a former Air Force pilot and a nuclear weapon officer. And maybe I could talk to him. It'd be really cool if we could get him to come on and talk about permissive action links.
That would be very interesting. I could see him not wanting to share very much of that.
Yeah, I know. That's the problem, is for him to try and figure out what he could talk about and not.
Yeah. One of the things I learned in my research is I'm sort of interested in the political effect that nuclear weapons have. I think that's really interesting. It really seems like nuclear weapons have been a big driving force for peace. It could be correlation and not causation, but it seems like once states become nuclear armed, they mostly stop fighting with each other. They still fight with each other through proxy wars. But it seems like in modern history, once you get the bomb, you also gain sovereignty, particularly from the US. As soon as you have nuclear weapons, the US is like, okay, all right, we're willing to negotiate with you now. We're not just going to invade you. And maybe if you're just shy of the bomb, they invade you. So I looked at what countries have had nuclear programs, and I thought I knew the list. So the nuclear club is the US.
Can I guess?
Oh, sure, go for it.
Okay. US, Britain, France, Russia, China. Formerly South Africa. I think they gave up their program, but they did, or it's rumored that they achieved a test cooperating with Israel, maybe.
Mm-hmm.
There's this long story about a satellite reading of an explosion. Maybe they achieved it.
Yeah.
I believe there were 8 total who today like openly have programs. It's still rumored whether or not Israel has nuclear weapons today, though I think it's kind of widely believed they do.
Yeah.
Who am I missing? Let's see, China, Russia, US, Britain, France. Who are the other big players? I thought there were 8. North Korea.
Mm-hmm.
I feel like there's some really obvious ones I'm missing here.
Yeah, kind of.
Who are the rest?
India and Pakistan.
Oh, yeah, of course.
Mm-hmm. Yeah, so I was like, okay, I think I know who's in the nuclear club, and I was able to sit down and just type it out, and then I went and verified it. Yes, that's right, that's the list. I got it. But then I went and looked at who has ever had canceled programs. And I thought, oh, well, South Africa, right? And Israel is of questionable status.
Yeah.
But it turns out, so there's Nazi Germany, of course.
Gaddafi had a program.
Yeah, so probably Norway, Sweden, South Africa, Israel, Iran, Japan, Brazil, Argentina, Italy, Iraq, Libya, Romania, and Switzerland.
Mm-hmm.
All those countries had at least semi-credible nuclear programs for some amount of time.
So do you feel that they abandoned those programs because of the difficulty in acquiring the fuel?
They abandoned it for different reasons. That was a huge one. South Africa in particular is the country I was thinking of when I was saying some countries had devices ready but no material. So South Africa was gearing up for a nuclear test. They were only working on the gun-type bombs, but they had the device ready. They just didn't have the uranium. And they even drilled some holes in the ground to be able to do tests in. And then I believe French and US intelligence detected that they were doing this. And so the US was like, whoa, stop. We don't want you to do that. Since probably a little after 64, I guess really, especially in 67, once they'd done their nth country study, the US realized that other countries gaining nuclear capability was only a matter of time. It wasn't really a matter of anything else. Like, eventually, given enough time, they would learn how to build a nuclear weapon, and then given a little more time, they would have enough material to be able to make one. And so that's where the US started getting all worried about proliferation, as they put it, which I think is a really funny term. Like, a lot of people think, oh, nuclear proliferation, that's really bad, right? And it's bad if you're the country that has nukes and the other countries are trying to get them. It's not so bad if you're one of the countries that feels defenseless and you're trying to achieve nukes. It's kind of like, is it better to be the only guy in your neighborhood with a gun, or to be one of the people who doesn't have a gun, and then that guy with the gun is like, I don't want the rest of you getting guns. I don't really like gun proliferation, but he won't put his gun down. So the US started getting really concerned, and through intelligence efforts and diplomatic efforts and sometimes military efforts, tried to get most other countries to stop working on their nuclear program. And sometimes other countries who were scared of them did that too. Like Israel bombed a reactor in Iraq, for instance, to try and hurt their nuclear program. So I didn't know about Sweden. It sounds like they were working on it basically since the end of World War II. It was like they opened the papers and it said, US bombs Japan with this new type of weapon, and they were like, we have to build one too. And then increasingly, they felt that they needed it to be able to withstand USSR's aggression, potentially. if that happened. And so they worked on that program until 1972, but they essentially gave up in 68 when they signed the Non-Proliferation Treaty, which is what the US was pushing around to other countries to try and get them to not proliferate. South Africa gave up in 67. Let's see. Iran is probably still secretly working on it, even though they've agreed to various treaties. Japan's program ended in 45. They were trying during World War II. I don't think they really were ever making a super credible effort. They just didn't have the resources. But they were definitely trying to maybe build a bomb. If it had been convenient, they probably would have made one. Brazil started in the 70s or 80s, and maybe Brazilian listeners will know more about this, but if I'm Brazil, I don't know who I'm going to bomb. I looked at a map of South America because I'm not super familiar with it, and it looks like Brazil borders nearly every country except for Peru and Chile, but I don't know which of those they would most feel animosity towards or feel animosity towards them. Maybe Venezuela invades or something, I don't know. But that seemed really strange to me. But that ended in 1990 with Non-Proliferation Treaty. Argentina worked on it for a little while in 1983. Italy worked on it in the 60s and 70s. They gave up in 75 with the Non-Proliferation Treaty. Iraq worked on it from 1959 to 1990. That'll probably be a contentious point because the US has a lot invested in representing Iraq as having weapons of mass destruction. But it looks like, similar to what North Korea's done, Saddam Hussein wanted Iraq to be nuclear capable. And it probably really would have changed the political landscape if the US had known Iraq to be nuclear capable and if they had conducted a test. I don't think they would have just invaded them like they did. They would have had to do something else. Libya had one from 69 to 2003. Romania had one in the 80s, and they gave up in 89. Switzerland had one from 45 to 88, similar to Sweden. They essentially were like, we have to start on this immediately. We might need it. And they signed the Non-Proliferation Treaty. So I had no idea before researching this how much impact that Non-Proliferation Treaty had had. I don't know what kind of leverage the US applied to these countries to get them to stop their programs. Or maybe that leverage wasn't even necessary. Maybe all the countries were like, this is really expensive and we want to quit, but we don't want to just quit for no reason because it looks like giving up.
What about Ukraine? I thought Ukraine had weapons after the USSR broke up and then they gave them to us, or they just kind of gave them up. They had Soviet weapons left over from the USSR and they kept them for a while.
Yeah, Ukraine had the third largest arsenal in the world. They had about a third of the Soviet arsenal. So yeah, there were lots and lots of weapons placed in Ukraine, but it looks like they were locked out by permissive action links. So they destroyed the weapons and they joined the Treaty of Non-Proliferation on Nuclear Weapons.
Okay.
So there's that treaty again. They destroyed them in 94.
I wasn't familiar with that detail that they were essentially bricked.
Yeah. That's why you should use open source software. Then you can fire your nuclear weapons.
Know what's on your device.
Yeah. But yeah, that treaty, everyone wants non-proliferation, apparently. I didn't realize that. I don't know what I thought, I guess, but I was a little surprised. Also, presumably, Saudi Arabia has an active program. And then there's a couple of countries, Mexico, Japan, like modern day Japan, and South Korea, that fall into the category of they're technically capable and industrialized nations, and they could probably gain nuclear capability very quickly, but they don't have any plans to do so. And it's a little weird that South Korea doesn't want to. Maybe they have the more pragmatic viewpoint of, well, what would we do with them? Because nuclear weapons are not the most targeted of weapons.
I wonder to what extent South Koreans may think that reunification is eventually possible.
Yeah, it probably is. I mean, I guess there's a scenario where North Korea diverges ever more from South Korea, but that doesn't really seem super likely to me. I don't know. Maybe we should do the podcast where we speculate about Korea, but let's see. Also, while researching the history, there was a guy in 1942 who sent a letter to Stalin, and he pointed out that no one had been publishing anything about fission since it was discovered, and all the main physicists who were involved in the discovery weren't publishing anything at all. And I thought it was really funny that someone discovered this through sort of this like absence of information. They're like, hey, wait a second, what happened? And he was like, I think the Soviet Union needs to start a nuclear program right now because I think this is really important. And they did.
You look for the silent hole in the water.
Yeah. So I thought that was pretty funny. The US went really hard on nuclear weapon detection. I assume they had a lot of espionage going on in all the countries they thought were soon to be nuclear capable. But it's, I think, most important to actually detect the test of a device. And so there's the Venona satellites, which is the thing you were thinking of. That's the South Africa, Israel, maybe joint project. Various sources are either like, oh, it totally was, or it totally wasn't. So, I don't know.
It's kind of like the WoW signal with Arecibo. And it's like, oh, that was definitely aliens. And other people are like, no, it was just a bird crapping on the antenna.
Yeah. Yeah, so the Venona satellites were looking for above-ground nuclear tests. And nuclear weapons always have this double flash. They're like flash and then like slower but also very bright flash. And the first one is where it detonates and it just releases a lot of light. And then later it heats up the air and produces a fireball. And so that can be detected from space. So the Venona satellites were just looking down at the Earth, presumably doing other useful intelligence activities, but they were looking for nuclear flashes. And that's what the US thought they saw. And no one can confirm or deny this. But the US also got really interested in seismic studies around the 50s, 60s, and 70s. And they were like, oh, it's really important that we monitor lots and lots of, earthquakes and things like that. But really, they were looking for below ground tests. And even now, when North Korea sets off a weapon, all these countries rush to report exactly what the yield was and what the magnitude of the earthquake was. And there's various seismic sensor networks all around the world. And they're trying to make it so that there's just nowhere you can hide a nuclear test. So all nuclear tests are effectively public to various governments because of that. So I don't know. I thought that was kind of funny because I've also read about how the US got really, really interested in radio telescopes around the time they wanted to do a whole bunch of radar-related espionage against the USSR. And so I remember thinking, like, why do they have this network of hydrophones and seismic sensors, and why invest so much in this? And it's for nuclear weapon testing detection.
Yeah.
Basically, after the US started testing weapons, it contaminated the entire world with fallout. And so now anyone who's produced an art forgery after about 1945 is going to have paint that contains nuclear fallout, thus marking it as a forgery. And so any artwork from before that won't have any. And it's just about impossible to find clean materials. Like, you'd have to, I don't know, go mine for it or something like that, and then keep it contaminant free. So it's just funny to think that there's just fallout in everything, and it's detectable.
I've read about that also, where they go and dive on ships that sunk before that to get steel that's not contaminated to use as
Right.
for some instruments that need to detect radiation or something like that. I forget the exact details.
Yeah. Also, you can look for clean materials to make things like RAM out of, so that it doesn't have as many nuclear decays in it.
Yeah.
Another thing that people often, I don't know what they're imagining, maybe they just haven't really thought of it, but there have been over 2,000 tests of nuclear weapons, like, since 1945. I think people often think, like, the US tested one, they set off two, there were a couple of other tests, like, I've seen pictures of them, and I guess the other countries tested a couple, but I think maybe if you were to ask people to estimate it, they'd come in at something like 30 tests or 50 worldwide, something like that. But instead, it's been thousands. Most of them were the US, but a few hundred of them with the USSR. And so it kind of provides some insight as to what it would take to accidentally destroy the world with nuclear weapons. Because you think, like, oh, what if 1,000 nukes got set off? Wouldn't that create, like, nuclear winter or something like that? But the answer is 1,000 nukes have already been set off. And for the most part, you can't really tell. You can detect a little bit of fallout and things, stuff like that, but they're not as environmentally devastating as I think some people imagine.
Would they not have been set off in ways to minimize those effects?
A lot of those tests are underground, or they're underwater,
Okay,
or something like that. But there were a fair number of atmospheric tests, and it was just like we're blowing it up in the atmosphere, and it just spreads fallout everywhere. The US sort of caused some disasters by doing that in a way that they shouldn't have. But after a while, there's not really a problem anymore. So the idea that if all the countries in the world set off all their nukes at once and it would just like destroy the world, I think that's a little bit overstating it. It would be really bad. It would be a very bad nuclear war. But I'm not sure that setting off all the nukes at the same time would really bring out an Armageddon type scenario in terms of what it would do to the Earth's biosphere. Obviously, it'd kill millions and millions of people, but I don't know. I wonder about that. I didn't do much more studying about that, but it's weird to think, like, what if thousands of nukes get set off and it's like, oh, that's already come to pass and you didn't even notice. Another thing that I didn't know about until I researched this is the US stopped making nuclear warheads in 1989. Did you know that?
I knew that our stockpile was old and that we had to refurbish them regularly.
Yeah. If I had to guess, I would have guessed that the US kept manufacturing them at a very low rate. But apparently the US just stopped. And so nuclear stockpiles around the world are just gradually dwindling. Countries keep end-of-lifing different weapons. They don't want to support that weapon anymore. They don't want to keep refreshing it. They don't want to support its delivery vehicle, whatever it is. Or they want to support it, but they just don't need that many. And so it seems like gradually most of the countries around the world are sort of disarming just because it's inconvenient to stay armed and it doesn't really pay off militarily.
Mm-hmm.
So that's cool. I was sort of a proponent of, like, I don't think the human race is going to kill itself through nuclear war, but I didn't really have as much evidence to back that up. But now, having looked at this, it seems a lot more far-fetched that people annihilate themselves through nuclear war. I think it might not even be technically possible right now. So, score one for humanity getting annihilated by strong AI.
My money's still on gamma ray burst.
Come on, gamma ray burst.
Okay, you want to talk about delivery systems and defense?
Oh, yeah.
Okay, so I'd like to talk about that some.
Sure.
So, we've had this whole dust up recently where North Korea set off a fusion device, which is a big deal.
Very impolite.
And they've also done a bunch of ICBM tests, intercontinental ballistic missiles, which have very long ranges. And so it's widely believed that they have an ICBM that's capable of hitting the west coast of the United States.
By west coast, do you mean Alaska?
I thought it extended down most of California. Do you know that to be otherwise?
No, I'm not sure.
Okay. I thought it included like LA and San Francisco and maybe not San Diego, maybe not that far south, but
eventually they'll get there.
Correct.
Just give them a few more years.
Yeah, that's not a big deal. So when you combine those things, and assuming that the weapon can be miniaturized and the delivery vehicle is reliable enough and that it can carry the weapon, then that gives North Korea the capability to deliver a large yielding weapon to American mainland. So something that happens from time to time when those kind of discussions start in the news media is that we start seeing all this footage of these missile intercepts, these tests that the military does where they shoot their own high altitude missile and then they have a intercept system that we've built and they intercept the high altitude missile that they've shot with their interceptor. And then they show us this great footage of this, one missile going down and one coming up and, maybe they don't show the actual explosion. I don't know. But, and then we all feel safe. And it's kind of like when the kids would shelter under their desk, like turtles, and they were safe from the Russians. And it's kind of all bullshit. So there's several reasons why. So the first big problem is that it's much easier for the attacker than the defender. And that generally goes for a lot of things when you talk about any type of fighting, not just warfare, but the attacker almost always has the advantage. So in this case, the reason he has the advantage is, let's say North Korea has an ICBM that can reach the west coast of America. And let's say they have one, and they have one copy of it. And let's say it's going to be reliable. So when they shoot it, it will get onto a terminal trajectory, putting it over its target within some, circular probability error or whatever, so that it will approximately hit where they're aiming. It's close enough. And that to whatever degree the guidance system is inaccurate, the yield of the bomb will make up for it. And it'll still kill a lot of people where they're aiming.
Okay.
Okay. So we don't exactly know where that'll be. And there are a lot of reasonably large population centers on the United States West Coast. There's the ones I mentioned in California, but there's also several in Oregon and Washington State too. And potentially some in Canada, but I don't think they would strike Canada. Everyone's so polite there.
Mm-hmm.
So the problem for us is we have these interceptor systems, but a system by virtue of an interceptor having to climb against gravity, having to intercept an incoming ICBM, it can only cover so large of an area. So if you have a battery, which will consist of various assets that track incoming ICBM, helping the interceptor to target it, helping to guide it onto the target during flight, and consists of one or more interceptor missiles, that battery is stationed somewhere, and it may be spread out over several hundred yards, or it may be, in a smaller area, just depending on what kind of blast you get from launching the missile, but the interceptor, I mean. But ultimately, you have this problem that if North Korea has one missile, they can fire at any of these large population centers. And we need many, many interceptor systems in order to defend all those possible targets.
Mm-hmm.
And then not only do we need multiple systems, but we have to account for things like, what if an interceptor fails to hit? Do we just fire one interceptor missile and place the entire bet on that one working perfectly? Or do you fire multiple ones in case the first one fails? Because if you fire one and then you wait to see if it fails, and then you decide to fire a second based on the first one working or not, you may not have enough time. And certainly if the first two fail, you probably don't have enough time for a third. So you need to fire several. So you need several of these missile batteries in one place capable of defending against an incoming ICBM.
Mm-hmm.
So you're at a huge disadvantage in that you have to spend a lot more effort to defend the area than North Korea would have to expend in order to threaten a huge area like the west coast of the United States. So that's the first big problem. So we're at a huge disadvantage there. And it's almost certain that we do not have enough missiles for that. Then you get into these other engineering problems of an ICBM coming in, it's essentially unpowered. It's falling from orbit.
Mm-hmm.
And so it's not going to fail and miss. Your interceptor is climbing against gravity. So if you have a motor failure, you're going to stop climbing, go ballistic, and probably not have enough delta V to still hit your target. So he has an advantage that there are several failure modes that he can have that still allow him to succeed in his mission of delivering a bomb. So when you go to actually intercept him, he's going very fast, and you have to have a guidance system with sensors accurate enough to guide you onto him and get very close so that you can have a warhead that can engage him. And the warhead problem is its own whole big mess. So when you have air-to-air missiles, they have what's called an annular warhead. And the way an annular warhead works is if you imagine laying out a whole bunch of metal rods. So imagine all these metal rods and you lay them out together parallel, and you take the ends of two of them that are next to each other and you weld them together. And then you go to the opposite end and you weld the next two together, and then back to the other end. And you're basically making this jagged pattern of welded rods connected to each other.
It's kind of like, it's like if you take a piece of paper and you cut a really long slit in it, and you cut another really long slit from the other side next to it, and you keep doing that, and you end up with this very long zigzag of paper out of one small sheet.
Yes. And so when you get to the end of these rods welded together, you fold them around in a circle and you weld it. And so what you can imagine is this metal structure that if you pulled it apart would make this very large ring. And it's made of a metal that's, kind of malleable, so it can do that. And then you put that around a core of explosives and you put that in an air-to-air missile. And so when you fire that against a plane in air-to-air combat, the goal is the missile seeks in on the heat from the exhaust from the engine of the plane you're engaging, and it guides it close to the plane, and then there's a sensor that decides, hey, this is close enough, I can explode here. It detonates the explosives that are within that annular warhead, and then when that explodes, those metal rods blow out into essentially a giant circle of metal. And the hope is that part of that circle of metal intersects the plane that you're attacking. And, there's not a lot of unnecessary stuff in a fighter plane, right? So you're going to cut hydraulic lines and electrical lines and fuel lines and airlines and, pilots and things like that. Anything you cut is essential. Mm-hmm. And so that's how an air-to-air warhead works. But if you imagine what kind of warhead might you need in an ICBM interceptor. So an annular warhead is probably not a good idea because you need to be very close when you hit. And the relative approach speeds of the interceptor to the ICBM are much, much higher than an anti-air missile to an airplane in air-to-air combat. And so the window within when you can detonate your warhead in order for the warhead to be effective is much, much narrower. And so you might think, well, why don't we build a fragmentation warhead? Well, it would have to be really big, and you need to be really close to the ICBM for part of it to hit. Mm-hmm. So I don't know what kind of warhead they actually use. Do you have any idea, Blake?
Well, I know the most recent things I've seen are generally kinetic kill vehicles, which is just a fancy way of saying they just try to ram into it directly.
Wow, so they do actually try to get the guidance problem solved so well that they just ram it.
Yeah, because I think that there's just not a lot of room in the warhead part of the problem to work with. So you just spend that mass on terminal guidance, and you just try to hit it.
Okay, so you just have radar guidance on board and provided from the ground too, uploaded.
Yeah, I have no idea what radar guidance looks like if you're trying to intercept it, like Mach 25 relative speed. And
yeah,
like your nose cone is superheated by what you're trying to do. Like, I don't know how that works.
So you have these issues, and then you have the problem that the ICBM can have countermeasures, and it could essentially do things like try and wobble around a little bit and make you try and match it, and hope that you have some kind of failure of your control surfaces so that you go into some degraded mode where you might not be able to match it well enough to hit. Mm-hmm. And all of these problems favor the attacker in an ICBM scenario.
It can also launch dummies. It can have multiple warheads in a single vehicle.
Yeah, and so that's something that was developed in the Cold War, was the MIRV, the Multiple Independent Reentry Vehicle. And so when it got up to apogee, or probably a little after apogee, and it started to re-enter, it would break open and it would be several nuclear weapons in their own re-entry vehicles. And at that point, you have to launch an interceptor for each one, because they're each going to be guided separately down to targets on the ground. Now, it's not apparent that North Korea has that ability yet, but they eventually will. Mm-hmm. And at that point, when you might say, well, if we just have, 5 missiles ready to defend San Francisco, we're safe. There's no chance that 5 will fail. Well, then they shoot a MIRV, and the MIRV splits open into, 3 or 6 or 10 independent reentry vehicles. Now you need 15 or 30 or 60 missiles in order to defend. Mm-hmm. And the nice thing for the attacker, again, is those don't all have to be nuclear weapons. Maybe one of them's a nuclear weapon and the rest are just dummies. And you can't afford to try and play Russian roulette with that. So you have to try to shoot all of them down.
I think it becomes Korean roulette then.
Yes. That's very insightful. I appreciate that. The problem is that all these things favor the Koreans, even at the point right now where they're essentially very primitive in both their nuclear and ICBM technology compared to us. The missile defense system is not something you should take a lot of solace in us having.
Mm-hmm.
I have very little faith in it defending against an ICBM. And when we see video on the news of, well, the military tested an intercept, well, they designed a test that they could pass. And would they ever tell us what kind of countermeasures did they use? What was the capability of their simulated ICBM? They're not going to tell us that, you know.
Well, usually the answer is no countermeasures. And the ICBM's coming in the most favorable trajectory. And they knew it would be there.
Well, yeah, the ICBM is targeted at the launch site of the interceptor.
Yeah, sometimes.
And so you have the most favorable thing. And so I was explaining this to a coworker this week, and I made an analogy, and I said, it is possible to take two guns and fire them and have the bullets hit each other in air. And you can actually look on Google. There are some really cool pictures of bullets that have been recovered from battlefields that were like that. And it's also possible that I can very carefully design a test where I take some electrically primed ammunition and I take two barrels and I bore sight the barrels so they're pointed right at each other. And I load the ammunition in and I run two equal lengths of wires to each of the pieces of ammunition, and I set up a circuit so that both of them are powered at the same time, and I build some kind of enclosure out of, bladders full of water approximately in the middle, in between the two barrels, but it's kind of like an arch so that there's air in between, but then there's all these water bladders around it to catch the resulting bullet that hits together. And then I can throw the switch, complete the circuit, the two bullets will fire, and they'll hit each other in the air, and they'll be caught in the water, and I can recover, and I can say, look, I hit a bullet with a bullet. And you'll say, that's awesome.
That's awesome.
And I'll say, now, do you want to hire me as a bodyguard? And you're probably going to say, well, no. And I'll say, but I have a handgun, and I can hit a bullet with a bullet. You just saw it. Like, here's the bullet, like, impacted into the other bullet. I recovered it even, and I have high-speed video.
Mm-hmm.
And yet it's a useless demonstration to my offer to be a bodyguard who would walk around with a handgun and protect you from an assailant by shooting bullets out of the air. And that's kind of an analogy that I put for ICBM missile defense, is that yes, in a very controlled test where we are the attacker and the defender, we can make some very nice footage.
Yeah.
But I have very little faith in ICBM missile defense.
Yeah. So I've also talked to my wife about this. She sent me an article from New York Times. If missiles are headed to Guam, here is what could stop them. And of course, it's just some missile defense systems. So I went ahead and did some research on those to figure out, like, what are their capabilities? Because, so initially I thought what probably a lot of people thought, which is, in the Persian Gulf War in 91, Patriots were shooting down Scuds all the time, right? Except they weren't. They were engaging them, which is easy. That's a missile is fired at another missile. And they intercepted them a fair amount. But what you don't know is that intercept means passed in flight. Like, if they pass nearby, that counts as an intercept. Like, I mean, technically it is, I guess. But what you think of from the military's use of the term is blew it up in midair. But as far as anyone can tell, no Patriot ever struck and destroyed a Scud. So in 91, where they had 40 different engagements, they probably never destroyed any of them. So then there's the THAAD system. It's THAAD. They performed a bunch of intercept tests on it. They had failure, another failure, failure, hit a test target in a simplified test scenario. For whatever good that does. Hit a test target outside the atmosphere. And that was in 1999. So, I mean, that's interesting, but a test target outside the atmosphere doesn't have to be traveling particularly fast or doing anything.
Wait, so THAAD is an ICBM defense. It's not a rocket defense like Patriot was.
Scuds are ballistic missiles. So Patriot was to stop that, but THAAD is meant for ICBMs, yeah.
Okay.
And so, in my opinion, all those tests look like not a full-scale test that proves it would actually work. And then there's the SM-3, which is another ICBM defense, and it appears to never have destroyed an MRBM or an ICBM in a test. And they use terms like intercept or successful test, but without defining what the objective was. So, as far as I can tell, there's at least 3 different technologies that the US has probably deployed that cannot intercept an ICBM. But as far as the press is concerned, there is a magical golden shield around the US that will block all missiles no matter what.
Now, is there a particular index fund I can short for this?
It's actually very difficult to bet on Armageddon. I think you end up needing to build an instrument that looks like a credit default swap. You could, though. Like, imagine an instrument where someone pays you X amount per day until a certain point at which you must pay them a much higher amount.
Yeah.
But, yeah, it's hard to short the apocalypse. But yeah, I agree with you. I don't put any stock in missile defense systems. It's an incredibly difficult problem. And I think there's also some economic and political incentives there. Like, yeah, there might be taxpayers under the missiles, but is it me, the politician, making the call that's under the missile? Like, I don't know. Maybe I'll just invest in bunkers and make sure that I'm in them when the missiles fly. If you have early warning detection and you have good bunkers and you have access to them, do you need missile defense? Everyone else needs missile defense, but they're not deciding how to spend the defense budget. So it's kind of a perverse incentive there. There's also sort of a destabilizing impact if you ever build a good missile defense system or try to imply that your missile defense system is good, because it implies I now have first strike capability and have removed your ability to retaliate. So it takes time to build a good missile defense system. And so another country can easily and rightfully say, well, maybe we should first strike you before you finish it, because otherwise we'll lose our capability to first strike ever again. And I get the impression that that happened between the USA and the USSR during the Cold War, where the US was like, oh, we're going to build this really good missile defense system. And the USSR was like, maybe we should shoot missiles at you then while we have the chance. And they had some tense negotiations around that, which ultimately led to lots of disarmament, but it could have gone a different way.
What about laser-based missile defense?
Yeah. So what do you think about that?
It, on the surface, it sounds promising, but I wonder if I'm just being stupid the way most people are about missile-based missile defense.
I don't think you're being stupid. It does travel at the speed of light, right? That's an advantage.
It seems like if you can get a high-powered beam and, you can solve the dispersion problems and those things, it seems like targeting shouldn't be that bad, because you just put out, a bunch of radar targeting from the ground. And is it interferometrically target using a bunch of sources?
Oh, yeah. I have no idea how to say that word.
Yeah. And basically you take a whole bunch of measurements from different places and you gain accuracy.
Mm-hmm.
And then you can aim very accurately at this missile that's coming in, and you just focus your laser on it for a while until, I guess, part of it gets hot enough, and probably it would just destabilize in flight, and then it would break up.
Yeah.
And maybe that would do it, unless the attacker then decides, well, I'll just make sure that the warhead is designed so that even if the rest of the vehicle breaks up, the warhead falls to the ground and it's okay. You still have to shoot all those down individually.
Yeah. I think the problem is the dispersion problem, like you said. I think that is really, really hard to solve, and it's a lot harder than people initially gave it credit for. And also, adding an ablative coating to your warhead gets you really far.
Okay. So the dispersion problem, if you don't know, is with lasers, when you shoot them, the beam spreads out over distance. And eventually you don't have a focused, nice beam anymore. And when you're talking about laser-based missile defense, you're going to be talking about trying to shoot this down essentially, I don't know, 100 or 200 miles over the Earth or something. Something very far at which the dispersion will be significant.
It could be only a few miles up.
I thought you wanted to detonate just like 2 or 3 miles up.
Well, as we talked about before, it probably won't detonate because nuclear weapons are sensitive, fickle beasts. So if you're able to do anything to it to damage it, then you're not going to get a full yield nuclear explosion.
Okay.
But, I mean, like, an example of that is we build re-entry vehicles all the time. Like, a lot of spacecraft have been a re-entry vehicle or had one or whatever. And the conditions that you experience during re-entry are super harsh. And so if you think, oh, I'm going to add a laser to it, that laser has to be really powerful to be harsher than re-entry into the Earth's atmosphere. And you also run into this problem where if you deliver a continuous beam, the layers of shielding that are vaporizing will also continue to absorb laser energy. Like, if you imagine I have a microsecond laser pulse of some intensity, and then I have another one that's 10x the intensity, you're not going to get a whole lot more ablation from the material that you're shooting because it will vaporize, and then you'll be shooting essentially into that cloud. So you can heat it up a lot more, but it doesn't matter because it's already not connected to the original material. And so you have to shoot lots and lots of pulses for a while. Like, one of the problems you run into with laser-based missile defense, you have to have a long time on target with your beam. And that's a much more difficult problem than just like shooting it once with one burst. That's easy to do with the targeting you were talking about, but holding it on there, having a beam tracking system and making sure it doesn't vibrate is really, really hard.
Okay.
And like, for people who don't know, one of the problems is as you're moving your beam, you'll use electric motors to retarget it or something like that. But if it's vibrating basically at all, it's diverging by enough like fractions of a minute arc that it's not hitting the target anymore. It's like the difference between shining a spotlight at something and shining a shaky spotlight at something. And if the spotlight's shaking enough, then it's not even that bright anymore. And we're essentially trying to conduct radiation up through the atmosphere to the missile, so it needs to be super bright from the missile's perspective.
So then, what about aircraft-based lasers? Much more shaky, but higher in the atmosphere.
Yeah, I know their solution is really short pulse durations, but I don't know. And how do you know when to put them up?
You just fly them like SAC did. You just fly planes all the time until peace with North Korea.
Yeah, it seems like your only real solution is make people not want to shoot ICBMs at you.
It's a solid solution.
Or massive second strike. Something I've always wondered about, though, is, you know, the US has all these missile silos with these people in them. And I mean, as I guess as seen in war games, in theory, they would be given this order to fire. Like, all right, you know, blow up several cities in the USSR because it's Armageddon here in the US. And I wonder how many of those people would fire. I know they've interviewed some people who used to be in missile command, and some of them were like, oh, I would absolutely do it because, like, it needs to be done. They would have already hit us. Like, it's the only thing we can do to, like, punish them. But I think other people who probably don't want to say anything are like, I probably wouldn't have fired it. Because I think if you reach a point where missiles are in the air, adding more missiles really doesn't do anyone a lot of good. It only does a whole lot of harm. It's like, turn your key and push the button and kill another 1,000,000 people. But, like, you're not going to win the war. You're just going to kill 1,000,000 people. And I wonder how much countries really had second strike capabilities compared to what they thought.
I would bet there are several biographies written by, is the word missileers?
I think so, yes.
That would probably talk about that specific issue and potentially the kind of training and selection they did to make sure that was not an issue. So I bet if you searched out biographies like that and read a couple, you might find your answer.
How do you select for people who will do something in a circumstance that's never, ever happened before?
I bet they thought a lot about it.
If you keep all of the details of your training secret and top secret, then you still have a credible threat, even if you don't believe that your missileers will actually fire.
I just don't feel like that's a problem.
Maybe not.
I don't feel like it would have come down to it, and a ton of guys would have suddenly been like, yeah, I just can't do it.
The only thing I can think of is you have training exercises that are indistinguishable from reality. You have no outside contact, and you're like, fire the missiles. And then they fire the missiles, and you're like, and then they come up at the end of their shift, and they're like, oh, the world wasn't destroyed. Good. And I think morale would be low. I know that morale was lower in that group of people than anywhere else in the Air Force.
Huh.
Well, babysitting a bunker all day is not really very interesting.
I joined to fly planes.
Now you get to fly missiles, but only once. And it'll be a really bad day.
Any other topics we need to hit on this?
Yeah, another one I thought was interesting. So, like, I was born in the 80s, so I've always lived in, like, the end of the Cold War and then what happened after that. And so I've always lived in an era where there were, like, hundreds of nukes and hundreds of nuclear missiles and mutually assured destruction, and everyone had this idea of, like, nuclear winter, and if you fired all the missiles, it would destroy everything. But there was this point where the US and the USSR were enemies, but they only had a few nuclear weapons. Initially, only the US had them, and then later, each country only had a few. So there was a point very early on in these tensions where a nuclear war was a practical and winnable type of conflict. The US could have bombed key cities in the USSR, and the USSR wouldn't have been able to respond in kind. And the US could have, I don't know, I guess invaded on foot in the USSR or something like that, or tried to get them to capitulate in some way. But that's something I thought was a very alien concept when I first heard about it, the idea of a winnable nuclear war. And then later someone pointed out to me that World War II was a nuclear war, and it was won with them. So I was like, yeah, that's technically correct, I suppose. But that was actually something that the US, it didn't exactly consider, but they drew up plans and said, what if we do this? And they're like, oh, the outcome would actually be really favorable to the US. But it's really good that they didn't, because probably it would have just murdered a lot of people for not a lot of gain. So I thought that was a little strange.
Yeah, I think people at that point in time did not have the stomach for it. If you want a really good article to read, the Berlin Airlift article on Wikipedia is exceptionally well written, and the subject is very good too. And there are several points in that article that really underscore how much people had lost their appetite for war by that point. I believe it was 1948. And the great lengths that everyone involved went through to try and posture, but still ultimately not go to war between the US and the Russians. And that nobody had the stomach for it at that point.
Yeah.
I would recommend that article to everyone. It's one of the best written Wikipedia articles I've ever read.
I'll have to reread it after this. Let's see. There were two incidents at Los Alamos during the Manhattan Project that I thought were, I guess funny isn't the right word, but...
So was one of them where the guy was holding the core apart with a screwdriver and it slipped?
Yeah. Yeah. So that guy was working with what was known as the Demon Core. That was Louis Slotin. And he had a core of plutonium that was just barely subcritical and two beryllium hemispheres. And the device was assembled where it was a beryllium hemisphere on the bottom, then the core, and then another beryllium hemisphere on the top, but not quite enclosing the assembly, I guess. Because if it enclosed the assembly, it would be critical.
Because the beryllium would reflect the neutrons back onto the core?
Yeah.
Okay.
And he was holding the hemisphere up with a screwdriver on the Demon Core, as it was known at the time. And the screwdriver slipped, and it assembled the device, and so it went prompt critical, which is, it's a criticality event. It's essentially increasing in the number of fissions per second. And so it irradiated everyone in the room, and in particular him, and he recognized what was happening, and then he disassembled the device very quickly. Good job for him. But then he ended up dying, a pretty painful radiation-related death afterwards. And they couldn't, like, tell his family what had happened or anything. And so I had always heard about this and this specific guy, and there's this picture that you can see online where it's like, here's where everyone was standing in the room at the time, and that was significant. And I was like, yeah, okay, I've heard about this accident. But then the thing that kind of struck me was the core was known as the Demon Core at the time. And I was like, well, why is that? And it's because there was a guy before Lewis Slotin, Harry Daghlian. I'm not sure if I'm saying his name right. And he was using the core, which was just known as a probably plutonium core at the time. And he was doing some different experiments with tungsten blocks. And he accidentally dropped a tungsten block onto the core, which reflected enough neutrons that it made it go prompt critical. And also, he recognized what happened, moved the tungsten block off, and then died as a result of the radiation. So, not to denigrate Lewis Slotin much, but you would think if you had this device where you're like imagine it explodes if you do a certain thing. You have this hemisphere of beryllium, this other one, you're like, if you put these two together, it'll blow up and it'll kill you. You would think you wouldn't hold them apart with a screwdriver and just like demonstrate it to people. You'd be like, if these go together, I'll die. Because that other guy died 9 months ago. And that's why we call it the demon core now. But apparently something made him say, I'm just going to screw around with this with the screwdriver. I don't really understand what was going into that.
And not only that, but a couple of the other people in the room died fairly soon after that, and several others died of cancer in the years following.
Yeah. It was kind of a bad accident, but like, was it really an accident? It was more negligence. But I don't know the mentality at the time. Maybe this was a really important experiment. Maybe getting really, really close to a criticality event was really important. I don't know. But I feel like if I were demoing stuff in front of like a classroom and the test article I was messing with was like a hand grenade, I would probably do something a little differently. I just thought that was really strange. Also, you mentioned duck and cover. Duck and cover actually works. If you duck and cover and there's a nuclear explosion, you're much more likely to survive or get less injured. However, there's a lot of ranges where you just get killed. But for people who are at the fringe, duck and cover really makes a difference. So, if you see the bright double flash of a nuclear weapon, just remember, duck and cover, and you're probably dead anyways.